Hi, and welcome back to what will be our second last video for Unit 3 for Chemistry. We are so close to the end. And so we'll be looking at Chapter 17, which is Energy from Food. So let's get started. Of course, the key place to start is with our key knowledge that VCAR expects us to understand. And we have 3 points here, one being the comparison of energy values of carbohydrates, proteins, and fats and oils, which we will use a table from our data book in order to be able to do and use for calculations. And the idea that glucose is the primary energy source, so we have to be able to write balanced thermochemical equations for cellular respiration, which explains how our bodies get energy. The final point will be covered in our next video, which is the principles of calorimetry, and we need to look at solution and bomb calorimetry, including the determination of a calibration factor, which moves a little bit on further from where we were in Unit 3, where we looked at calorimetry simply for that determining the amount of energy burnt from a fuel. And also, of course, the considerations experimentally of the loss of heat. So in this unit, it is important for us to keep in mind some information from Unit 3, that being the idea of exothermic and endothermic reactions. Exothermic increasing the temperature of the environment, so releasing energy, and endothermic requiring energy, so absorbing energy to go in, and the associated energy level diagrams. Our definition of enthalpy for the calculation enthalpy being that the enthalpy of the reaction is the enthalpy of the products minus the change in enthalpy of the reactants. Remembering that thermochemical equations are balanced chemical equations where delta H is included, and we also need to give the sign of delta H along with the fully balanced chemical equation. That we change the sign for the forward and backward reaction. So if the forward reaction is exothermic, it will be negative, and the reverse reaction will be an endothermic process. Those signs change, but the magnitude of the enthalpy stays the same. That the relationship between delta H and the number of mole leads us to this equation here, which can be rearranged to give us N is equal to E divided by delta H. Okay, remembering that in this case energy will need to be in kilojoules, and this is kilojoules per mole. And of course, using our Q equals MC delta T equation. So they're the things that we need to keep in mind from Unit 3 that are expected to be known as we go through these topics. So we've been concentrating on food, and we know that from Unit 3, fuels are compounds that can be burnt or combusted to produce energy in exothermic reactions. Food provides the energy source or fuel for the processes inside cells. Same kind of thing, we are talking combustion reactions of these, or at least redox processes, but of course without the fire. Carbohydrates form the main energy source for the body, okay, remembering that they are polymers of glucose, and glucose is the main energy source, so they're our most ready form of energy. And these are used in preference to fats and oils. Glucose is the primary reactant in cellular respiration, and cellular respiration is the process by which we get energy. So all plants and animals acquire energy through cellular respiration. And this can be thought of in terms of a combustion reaction where either sufficient oxygen for complete combustion, or in the case of anaerobic respiration, incomplete combustion. Remembering anaerobic is without air. So aerobic respiration requires oxygen and is the main source of energy production for humans. Anaerobic respiration does occur in humans. This occurs in our muscles during long periods of exercise. It doesn't require oxygen, and overall it provides less energy, but can give us a burst when we're using energy in our muscles. Okay, so key things to remember for anaerobic and aerobic. The reactants are glucose for both, but aerobic also has oxygen. When we think about these, we will be writing the combustions equations for glucose, and it is incomplete for anaerobic and complete combustion for aerobic. we get a low energy yield for anaerobic with a high energy yield for aerobic. Anaerobic, we are looking at the production of ethanol and CO2, which we saw in Unit 3. And in animals, this produces a high lactic acid buildup in muscles, which is responsible for muscle cramps during long endurance exercise. And of course, if combustion is complete, we're looking at CO2 and H2O for aerobic respiration. So you do need to know these equations. The C6H12O6 aqueous, because we are inside cells, plus 6O2 gas goes to 6H2O liquid plus 6CO2, and we can see here that the delta H, making this a thermochemical equation, negative telling us that the energy is given out, and it's 2,860 kilojoules per mole of glucose. This is in comparison to anaerobic respiration in humans, where we have the C6H12O6 producing 2 equivalents of lactic acid. Okay, or this is the anion of the lactic acids, the lactate ions, because the acid here has been given up its protons, 2H+. As we can see here, this gives off a much lower amount of energy with only 120 kilojoules per mole compared to the 2,860 of aerobic. In yeast, remembering this is the one from Unit 3 that we need to remember for the production of bioethanol, we have glucose producing 2 ethanol molecules and CO2, and only producing 69 kilojoules per mole of glucose in that case. So each of the 3 nutrient types provides a different quantity of energy. The energy content of food is measured in kilojoules per gram or kilojoules per 100 grams rather than kilojoules per mole, because food is not a pure substance, so we can't get a per mole quantity for it. Remembering also the polymers of starch don't have necessarily fixed numbers of glucose molecules, we're talking thousands, so we can't get per mole. So we're talking kilojoules per gram or kilojoules per 100 grams, and is defined as the energy content of food when it's per mass. For most foods, the energy released is similar to the energy released during combustion, as that is respiration, and essentially we are looking at the oxidation of nutrients. Each of the major nutrients are given a particular heat of combustion in the data booklet, and there may be differences between mono, di, and polysaccharides in the carbohydrates. They are generalized. The energy available to the body from a nutrient or food is called its energy value. Okay, and you can see here that the energy value for fats and oils is lower than the energy content. Same with proteins. The energy value is lower than the energy content of proteins. Whereas for carbohydrates, they're pretty much the same. Because fats and oils have a higher value than proteins and carbohydrates, this is because carbohydrates and proteins already contain more oxygen atoms. They have already been partially oxidized. So the fats and oils have a greater potential for oxidation and the release of energy on combustion. However, we generally don't see that within the body, okay? So looking at specific cases for the energy value and energy content, we're going to do a comparison of a trisaccharide and a fatty acid, showing the differences in enthalpy caused by the lower oxidation content of the fatty acid. So we can see here that we have a C18H32O16 and C18H32O2. The linoleic acid has the lower energy content, okay? So, the lower oxygen content, it is more capable of being oxidized, i.e. a greater level of oxidation will occur, and we can see that by the amount of oxygen going in, and will produce a greater amount of energy per mole. The oxidation of the trisaccharide, however, requires 18 oxygen. We are seeing a lower amount of oxidation, and as a result, we see a lower amount of energy being given off. So the energy released by the combustion is often greater than the energy available for human food. So if we were to eat it versus burning it, we see less energy. These can be caused due to a number of reasons. Incomplete absorption of the nutrients after digestion, incomplete oxidation of these by things such as proteins, and of course insoluble fiber, remembering that insoluble fiber may be recorded in our mass of carbohydrates. Heat loss during the process of determining the energy. So not all of the energy released by oxidation during respiration is available for use in cells. Some is lost as heat, just the same as if we were doing it in a lab. The difference in energy available for the body is quite high in carbohydrates, because starch can be readily digested by humans and transformed into energy, and cellulose can't. So depending on the percentage of cellulose in the carbohydrate content listed in the food will determine how much energy we can get from it. Let's look at a couple of example calculations. These ones are directly from your textbook. So this one says that the labeling on a sample of unsalted cashews indicates that they contain 29% carbohydrates, 18% protein, and 46% fat. The remaining 7% is water, which does not supply any energy. We're asked to calculate the value of the cashews in kilojoules per gram. So if we assume 100 grams, okay, then we can start to work this out. So we would have 29 grams of carbohydrates, 18 grams of protein, and 46 grams of fat. So if we assume that there is 100 grams of the sample and each one is then contributing, we can work out the total. And we will use the values that are given in the data booklet. So in this case, we will have 29 grams of carbohydrates at 17 kilojoules per gram. In your data booklet, it gives it as 16, but we'll go with this one that is being provided here. We will have 18 grams of protein at 17 kilojoules per gram. And we will have 46 grams of fat at 37 kilojoules per gram. So we're just going to take the number of grams and multiply by the energy per gram. So 17 times 29 is 493. 18 times 17, 306. And our last one, our fat, 46 times 37 is 1702. Then we will add all those together. And what we end up with is a total of 2501 kilojoules per 100 grams. Because remember, we worked this out per 100 grams. So overall, we will have 25 going to two significant figures, because we're going to divide by 100. 25 kilojoules per gram is the amount of energy present in the cashews from each of the different food groups. Okay, so we find the sum of the energies and then divide by 100 to find the final kilojoules per gram. And that is indeed what we saw, keeping to the right number of significant figures. Okay, so now let's have a look at how this will appear in a question from VCAA. And this is a multiple choice question. So we're told that the following table contains the percentage composition by mass of the nutritional value of some common foods. Each one is broken down into carbohydrates, fats, and oils, and protein. We have fish, bread, cheese, and milk. We're asked which one of the following servings has the highest energy content. And we're given 100 grams of fish, 80 grams of bread, 40 grams of cheese, and 258 grams or 250 mils of milk. I want you guys to have a go at this question and then come back to see the answer. Okay, so hopefully the first thing you did was look for the energy content per gram for each of per 100 grams for each of the foods, and you would have seen that it was 16, 37, and 17 respectively. We can then just take each of the percentages, assuming 100, and multiply by those values and add them together. It means that 100 grams of fish would be 789 kilojoules. For the bread, we would get 1,084 for 100 grams. So 1,084 divided by 100 gives me the amount per gram. Multiply by the number of grams that I have in the serving that was told to me in the question, which is 80, gives me 867. For the cheese, when I multiply these out and add them all together, I get 1,699 divided by 100 grams, because that's the energy per 100, and then multiplied by 40, which is the number of grams that I want, gives me 680. 279 divided by 100 multiplied by 258 gives me 720. So the one with the highest energy content for the serving size specified will be bread, 80 grams of bread with 867 kilojoules per 80 grams. Okay, that's it for this video. Next one will be calorimetry, and that's the last one for the course for the year.